class. This is Miss Tina. I'm back again. I'm here to discuss Chapter 13, How to Interpret a 12-Lead ECG, but we're determining if there is any bundle branch blocks. Bundle branch blocks sounds intimidating, but it's not really. It's just looking at certain pinpoint leads to determine if you have a bundle branch block or not. So let's take a look. The first type of bundle branch block I will help you determine is to see if they are any right bundle branch blocks, or RBBB as we call them for short. In order to determine if we have a right bundle branch block, we're first going to look at lead V1. Now the reason why we're going to look at V1 because it is, if you remember how you lay out your electrodes, V1 is on the right side of your heart. So if there is a block occurring anywhere on the right side, V1 will pick that up when you do an ECG tracing. So what we're looking for in V1's printout or tracing is we're looking at the QRS complex. That's what we're concentrating on. So we're going to first measure to see if our QRS complex for some other reason is greater than or equal to 0.12 seconds. If you find out that it is, if it's yes, that it is greater than or equal to 0.12 seconds, we're going to take a look at the shape of the QRS complex and to see if it makes an M, the letter M, or what we call rabbit ears or antennae. And it has the RSR prime figure as you see on the picture on the right, and as it labels. And we're also seeing if our T wave is going in the opposite direction of our RSR wave, or RSR prime wave, sorry. If they are and it fits that criteria, then 9 out of 10 we have a right bundle branch block that is occurring. Now, as always, there's two halves to a whole. We just looked at the right side. Now let's see if we need to do to see if we might have a possible left bundle branch block. So if we have a possibility of left bundle branch block or LBBB, it's a little bit different from a right BBB. So instead of looking for an RSR prime in V1, we're going to look in V1 at the QRS complex to see if it makes an RS wave, where R, as in the picture on the right, shows a deep S in V1. And of course, we have to measure to see if our QRS is greater than or equal to 0.12. So if we fit all those criteria, we have an RS wave or either a deep S wave in V1, then we have a possible LBBB possibility. Because what ends up happening, if you take a look at V6, which V6 is on the latter half of the left side, correct? So if we look at our V6 and it makes, what do you think? The little rabbit ears, then we know we have a bundle branch block that is occurring, a left bundle branch block that's occurring. So it's going to be like the opposite of a right bundle branch block. Now with some cases, whenever we have a right bundle branch block, sometimes we will also have a hemi block. And what are hemi blocks? Well, hemi blocks are what we call bifascicular blocks, because not only do you have a right bundle branch block, but one of the fascicles is also blocked as well. And we have a left interior hemi block and a left posterior hemi block. So either one of those fascicles can be blocked, and it causes you to have a hemi block. So Let's see how we determine if we have a left anterior hemiblock. Again, it, don't get intimidated when we say how to interpret a 12 lead ECG. We don't look at necessarily all 12 leads. We look at pinpointed leads to see where the issue is occurring. Take, for instance, if we're looking for axis deviation. Axis deviation, we're only looking at two specific leads. We're looking at lead 1 and we're looking at AVF. Two leads out of that whole 12 leads. Same thing with a bundle branch block. We're looking at V1 and V6. More so V1 than V6. And if we are looking at V6, we're just looking to see what the opposites are, but mostly V1. With a hemi block, we're looking to see, first of all, determine if we have a right bundle branch block. Not all right bundle branch blocks are going to have a hemi block. Just remember that. But to determine if we have one, we first have to determine we have a right bundle branch block. If we have a right bundle branch block, we also have to determine the axis of that bundle branch block. So say if we are looking to see if we have a left anterior hemiblock. Well, in order to have a left anterior hemiblock, we have to have a right axis deviation. Then we're going to look at leads 1 and 3, as you see on the picture on the right. You would then follow these steps in order to determine if you have a left anterior hemiblock. So if in lead 1, as shown in the picture on the right, there is a small Q wave and a big R wave, along with, and in lead 3, there's a small R and a deep S, then you guessed it, we have a left anterior hemiblock. Simple. You're just looking at two leads after you determine if you have a right bundle branch block or not. So now let's take a look to see if we have a left posterior bundle branch block. If we see, as shown here, we have a small R and a deep S in lead 1 and a small Q big R in lead 3, then we have a left posterior hemiblock. So it's just something simple, easy peasy. All you're looking at is pinpointing two different leads out on a 12 lead read to determine if we have a right bundle branch block or a left bundle branch block. We're determining if we do have a right bundle branch block, if we have a possible hemi block, and there can either be a left anterior hemi block or a left posterior hemi block. Now, there is an algorithm that works wonders. It helps a lot. It's easy to look at and everything else. So basically with the bundle branch algorithm, it's asking you in V1 to see if your QRS is greater than or equal to 0.12. So if you answer yes, it indicates that we possibly might have a BBB, but which kind? Is it a right or is it a left? So if we look at V1 and we see an RSR prime like these pictures here, then we have a what? Yep, you're right. A right bundle branch block may be present. Next, we always have, whenever we see a right bundle branch block, remember, it's also associated with a hemi block. So now we have to determine if it's a RAD or a LAD, which is a right axis deviation or a left axis deviation. If it's a right and it fits these criteria in these 1 and 3, then we have a left posterior hemi block. If it's a LAD or left axis deviation and it fits these criteria, then we possibly might have a left anterior hemi block. But remember, not all right bundle branch blocks has a hemi block. because if they don't match these criteria, then we don't have one. So if we have a left, we just stop right there. Now, what if the QRS isn't greater than, and it's no, then we don't have a bundle branch block. But we can sometimes have a heme block without a right bundle branch block. See, not all right bundle branch blocks have a heme block, but not all heme blocks have a right bundle branch block. See, also, so kind of goes 50-50 halfway. If there's no bundle branch block and we have a rad or lab, we still have to determine if we have a possible heme block associated also. So this algorithm will be your Bible in order to determine bundle branch blocks and heme blocks. This is the easiest way, and it gives you all the clues and to looking for bundle branch blocks and heme blocks. I just want to thank you, and this concludes our discussion on bundle branch blocks. I do have a upcoming PowerPoint lecture video that will be coming up about ventricular hypertrophies. I would like to thank you for subscribing to my YouTube channel, and I'll see you next time. Thanks. Bye.